So we use this integral to help us deal with non-periodic exciting forces. That's what this whole chapter has been about, in terms of Fourier transforms and Fourier spectrums, or frequency spectrums. The simplest form of a non-periodic exciting force is an impulse. Okay, we covered the impulse last week as well, where you've got a thing of infinitesimally small width, okay, which will obviously have infinite height. And if you have a unit impulse, then the area underneath that curve, in a sense, is 1. Now, it's not a realistic function. Okay, it's merely a sort of mathematical concept that we can use to help us describe what's going on here. Now, level 1 dynamics, you covered what an impulse was. In fact, it may have been me that taught you. Okay, impulse is you've got a force times the time, which gives you a pulse. But as the delta t goes to 0, as it limits, it goes to 0, you get what's known as an impulse. And an impulse is the change in momentum. Okay, mx2 dot minus mx1 dot, where x1 dot is the momentum before the impulse, is the velocity before the impulse, and x2 dot is the velocity afterwards. Okay, now we covered that in, like I said, level 1 dynamics. And as I said, a unit impulse equals 1. So the change in momentum after application of a unit impulse will be 1. F delta t becomes 1. Now, if we had a mass spring damper system, okay, so here mx double dot plus cx dot plus kx equals 0. That's for a free system, okay, equals 0. We know the equation of motion. This is from chapter 2. Can be written like this. This is in terms of initial conditions, okay? We've got x naught here, x dot naught here, x naught here, okay? We've got damping in the system, so there's the decaying exponential, and we have omega d as opposed to omega naught in the sinusoid, because it's going to oscillate with a frequency of omega d being damped, okay? That's from chapter 2. We went through the derivation of that a number of weeks ago. And obviously there's various terms in this equation. We've got omega n, or omega naught, in fact, I should have written. Naughty me, okay? Omega naught is root k upon m. Zeta is c upon 2 root mk. There's a zeta, and there's a zeta, and then omega d is omega naught 1 minus zeta squared. Again, all stuff from chapter 2. Apologies, this should be omega naught, okay? I'm confusing my subscripts. A lot of resources do use omega n. Now, if we took that solution, so there's the solution, I've just copied it over to the next slide. If the mass is at rest at time is less than 0, so we're going along from negative infinity to 0, the mass is at rest, okay? And then we apply a unit impulse at time equals 0. So at time equals 0, you've got this impulse force being applied, okay? And then obviously afterwards, that force is not being applied anymore. So we've got, if you take the 1 is the change in momentum, so mx dot when time is 0, okay, equals 1, minus, and then we've got this mx dot as time is less than 0. Well, there's no velocity, it's at rest when time is less than 0. So you've got 1 equals mx dot, which is over here. X dot naught is at time equals 0. And so if we take 1 equals mx dot and we divide both sides by m, we get x dot naught equals 1 over m. And if you apply those two initial conditions to this equation, x naught is 0, so that drops out. Okay, that term there drops out. X dot naught is 1 upon m, so we've got 1 over m times omega d, sine omega dt times, and then you've got your exponential as well that you can't neglect. And this function here is known as the impulse response function. And it's the response of a free damped system, mass spring damper system, to a unit impulse force. Okay? It's an impulse response function, is what this thing is. Okay, and what we'll do is I'll plot it. So here we go. Here's our time domain signal, okay? You come along, you've got your impulse. I've drawn it here with a width, but obviously what really happens is this delta t is approaching 0. Okay, but it's to give you an idea. So you apply this force to your system, and this is the response of the system. You get this function. That curve is defined by that function there. I drew this in MATLAB, and I used that equation in MATLAB to give that curve. Okay. These bounding curves are given by the exponential. It's decaying exponentially. And this is my x, my displacement, and I've called this function, this particular function, g of t. Okay. I've just called it g of t. So if you have a mass being damper system and you give it an impulse force, this is the sort of response you're going to look for. Okay? Depending on the value of k and m and damping and all that sort of stuff, you'll get a different shape, but essentially you'll get a force that looks a little bit like that. Okay? The frequency might be really high, it might be really low. It depends on those values, characteristics of the system. But if you give it an impulse, it's going to respond like that. If it wasn't a unit impulse, but it was an impulse of magnitude f naught, okay, then the initial velocity is f naught upon m as opposed to 1 upon m, and you get a response that looks like that, which is exactly the same as g of t, but it's multiplied by that force. Okay. And so we can plot that again. Okay. So it's the same thing. This time f delta t is f naught as opposed to 1. Okay. And obviously this thing is going to give a response that's very similar, except for this time we've got f naught times by the response. So whereas this point might have been 1 on the previous one, it's now f naught, for example. Okay. So it's either going to grow or shrink depending on what the magnitude of f naught is. This is the general case. And this is really useful because imagine you've got some forcing function. Let's do some drawing. Let's hope it. You've got a forcing function that looks like this, okay? For example. You can divide each of these forcing functions into impulses. They're going to have impulses of different magnitude. But say I took one here, and this is a time equals tau for argument's sake. This is f of t. There's an impulse that is associated with that time. And if I apply that impulse at time equals 0, I get that response. Now you can imagine if I apply that impulse at time equals tau, so let's draw it over here. This is tau. Whoops, let's erase that. I meant to write tau. Okay, I'm going to get a response that's aligned in here that looks exactly like this. Okay. I could do it in red. How about that as a plan? I'm just going to draw it in red. Okay, so you just shift the response over to where time equals tau. We've got tau down here. And I'll show you that in a second. So mathematically, let's come out of here, let's close that. If we apply an impulse at an arbitrary time where time equals tau, it will change the velocity at t equals tau by an amount f naught upon m. Okay, that's mathematically what's going on. Okay, assuming that x equals 0 until the impulse is applied, so we've got no impulse at time equals 0 now, we've just got an impulse at time equals tau. Okay, it's given by that, f t minus tau. Okay, we're moving it to the right by tau, and so you get exactly what I drew here. Okay, so here's f naught. Okay, at time equals tau. So at time equals tau, we've got the thing as at rest, then you apply, then it responds in the way that it does to an impulse. Okay. And what you can do, if you went back to that picture of all those things, is you can take all those impulse response functions and add them all up, and you get the complete solution for whatever function shape you've got. Okay? So your arbitrary force can be assumed to be made up of a series of impulses of varying magnitude. Okay? They might be 1, it might be whatever, but it will be a certain force level magnitude. Assuming that at time tau, you get a force of f of tau, okay, because f is a function of time, at time equals tau, you get a certain force. That's the magnitude of your impulse, and it's acting on the system for the period of time delta tau, okay? So as delta tau approaches 0, you get your impulse. There's your impulse force. The impulse acting at t equals tau is given by f t delta tau, okay? So that's, like I said, you've got your force, it's an impulse, so delta tau is approaching 0, and that impulse is given by f delta t, which you've seen before, okay? And for any time t elapsed since the impulse is t minus tau, okay? So if you take time as 1 second, obviously if the force is being applied at 2 seconds, then t minus tau, 1 minus 2, you're 1 minus a second, you're a second before it, okay? Obviously t will pass through it, and then t will continue onwards. When t is 10 seconds, you're going to be 8 seconds to the right-hand side of your tau, okay? So the response of the system at t, so any t, due to this impulse alone is given by that, okay? So x of any time is going to be my impulse function at time equals tau, times by my response function of t minus tau, okay? X of t, which is the response, is going to be that impulse multiplied by my impulse response function, but at a later time, okay? So if I took, like I said, if tau was 2 seconds, so at 2 seconds I have a impulse that's being applied, okay? My response function at, say, 10 seconds will be that impulse multiplied by that impulse response function when this is 10 minus 2, so you're going to be a bit further down from where the impulse has been applied. Let me go back to the picture. Okay? Let's say that this is being applied at, say, 4 seconds. Okay? My response, say, at 10 seconds, which is over here somewhere, okay, we can see what the response looks like, but essentially it comes along, time increases, suddenly at 4 seconds it gives an impulse, the thing starts oscillating, and at 10 seconds, which is what I'm interested in, x of 10, bang, there's my response. And that line curve is given by that equation, where f naught is my impulse. Okay? F naught is f delta t. So I'm just writing what this graph is saying in mathematical form. There's my impulse, and there's my impulse response. So x of, say, 10, f of 2, delta tau, okay, is my impulse response function 10 seconds after, no, in fact 8 seconds after, 10 minus 2 is 8, 8 seconds after it's been applied. Okay, that's what that's saying. Now obviously if you've got a continuous force or a force that's varying in time, you can take all of these together and just add them all up. The sum of these is going to give you your complete force function for all time. Okay? So I've just taken that term, I've moved the delta t out here, because you'll see why in a second, okay? And I've got my force function and my impulse response function. And it's shifted over, depending on what my value for tau is, when that impulse is being applied. So you take all those things, you add them all up together, and you get the response. Now obviously what you can do is as delta t approaches 0, and you can replace the summation with an integral, and you get this equation. There we are. So I've just replaced that with an integral. That's gone approaching 0, so I've got it as an integration. And then if you make the substitution for for gt minus tau, that was way back on an earlier slide, we saw that substitution, so I've replaced this bit with my impulse response function, which is on that slide there. There's my F0 GT. Okay, so I've replaced it on that slide. And that's the equation that you got on page 144. Okay, so there's the derivation of it. And that is known as the convolution integral, or the Duhamel integral. And what this does is, if you know your forcing function, if that's going to follow a certain format, you can apply that integral and you get the response. Okay, you'll see that in a second. I'm going to do an example that we did back in chapter 3 to show that that's the response. The response you get is the one you know of. Okay. And it's very useful if you know what f of t is, if you know the analytical function of f of t, you can find the solution. Okay? And that's for periodic signals, non-periodic signals, whatever you want. You'll get it. Okay? Obviously, if your f of t is of some function you don't have the equation for, you then have to use this equation, but you have to derive it numerically, okay, using numerical methods, which you've probably covered before in maths and things like that, where you break it up into small steps and you do it numerically. So it's called the convolution or Duhamel convolution or Duhamel integral. If f of t, so this bit here, if that permits integration, then you can solve the integral, okay? Or if it doesn't permit integration, such as you've got a function where you know the shape, but you don't know what the actual equation is, then you have to use numerical methods to solve it. But like I said, based on this equation, it's not that difficult. So let's do an example of this using this equation. So as an example, okay, so we'll call this convolution integral example. As a basic example, let's do there is my non-periodic function, okay? This is f of t. This value, I'm going to give a value of f0 here, and we'll call this value t0. Now the equation for let's assume that our equation is undamped. So the convolution integral is slightly different from the one I've derived. We lose the exponential, obviously, because there's no damping, and we end up with an oscillation sine of omega naught t minus tau d tau. So that's the convolution integral that we had, but notice the exponential's gone, and in terms of sine being omega d times by t, we've got omega naught times by t, because it's obviously it's going to oscillate in an undamped frequency. So this function defined analytically, f of tau, is f0 between 0, tau, and t0. Okay, and it's 0 for t tau is greater than t0. Okay, there's obviously 0 before then as well. I've got 0 here. So there's two domains. There's a domain between 0 and t0, and there's a domain from t0 onwards. And what we do is we have to apply this integral for both of those domains. So for the first domain, for 0, is less than or equal to t, which is less than or equal to t0. Okay, x of t is f0 multiplied there. Okay, m omega naught integral between 0 and t of sine omega naught t minus tau. Okay, because f naught is a function, that can come out, which is why it's here. Okay, and we just have to integrate this bit here with respect to tau. You get that, okay, and obviously knowing that omega naught is root k upon m, you can then replace this with f naught divided by k, 1 minus cosine omega naught t. Now you've seen that before. Rectangular forcing function, so imagine that it doesn't end, okay, it just continues on, okay, you get that function. You can look that up in chapter 2, we derived it in chapter 2. There it is. Okay, and if you did want to spend the time doing integration, it's there, okay. I didn't write it down in my notes, and so to spend time doing it is not worth it. But you can do it if you wish to. And you'll find that it equals 1 minus cosine omega naught t divided by omega naught. Okay, so then for the second domain, for t is greater than t naught, x of t So if you go through the sums, this is the solution you will get. Cosine omega naught, t minus t naught, t naught, minus cosine omega naught t. So that's an example of how you use that integral to solve to get the equations of motion. Here we've seen that equation of motion before. We went back in chapter 1, we solved, chapter 3, we went through the solution to get that answer, okay? And this is showing you how with a non-periodic function, which is this rectangular function, you get a complete solution.